Am I audible? Yeah. Respected listeners, especially students, really excited to see, okay, some of them left still, really excited to see younger faces in this auditorium. I am also really excited because you heard about many of the applications that you can really do making use of the space technology, the spacecrafts, the science. Why all we do this? Why we don't we stand on the earth and do all these things? Why we go to space? You know, space is a vantage point. When you stand there and look at Earth, look beyond, you can see much clearer, much wider view of things. That's why space is important to all of you. And to go to space, you have no other way today known other than chemical rocket propulsion technology. This is a issue today. The Earth is pulling us all down, and if you have to cross that gravity field and get out of the gravity field, get into an orbit, or even get out of that gravity field, go to another planet, go to Moon, Mars, rocket is the only way. There is yet another view we need to take, that even if, when you look at as a country, India, this technology with you. You need to have in your country, to have your own launch vehicle, to have your own spacecraft and launch it from your own land. This capability is strategic capability, and that is a criticality of launch vehicle technology. Before I proceed on what I want to present today to you, I would like to talk only a very few areas. I am not going to talk too much on the technology aspect, but I would like to talk about our launch vehicles and how it is going to evolve over time, and what is the thinking process that is going behind the organization in building up this capability in India towards, one is improved capability, much higher payloads we need to lift to the orbit, and that too must be done with lesser and lesser cost, so that we will be able to really compete in the world. The exciting mission which is coming up in this February 2017 is a launch of PSLV C-37. It is exciting because it is going to carry the largest ever number of satellites in this mission. We have the Cartosat 2D, ISRO satellite, and INS-1A and 1B, two microsatellites of ISRO will be launched in this mission, along with 100 small satellites, microsatellites. You look at the way it is arranged there in this launch vehicle. Inside the payload fairing, we call the heat shield. They are all distributed, packed and kept in cold quad packs. And while we separate them, there is a separate sequence we have developed, so all these spacecrafts can be separated without collision. It's going to be an exciting mission. Watch out for this in the TV. The PSLV is a very unique launch vehicle. You know, it has been successively successful after its first failure, and we have done enormous number of combinations of satellite launches. See the varieties of mounting configurations of the spacecraft that we have created, dispensing systems that we have created enable launching. Not only our satellites, almost 122 satellites have been launched by PSLV, out of which 78 are foreign satellites. And with these launches of this another 103, the number is going to make a quantum jump. Recently, we have done a restart of an upper stage of the PSLV. The fourth stage, after injecting a satellite, it is fired again, it moves to another orbit, and then put another satellites. So it gives you a unique opportunity that in the same mission, you can do multiple orbital injection, which meets various mission requirements. It is continuing to remain as a workhorse of ISRO, PSLV. We have been launching one or two at least few years back. Last year we have launched 6 PSLVs, and in the coming years we are going to increase to 8 and then to 12 and to 20 progressively when we create industrial infrastructure. As you know, today to build these satellites, launch vehicles within ISRO and using the industry support, we have really a constrained, resource constraint, but our government and the organization is looking at forward to the industries to come up with models where they can build and create a capability within the country and launch them. We have shown the way how it can be done, and we are waiting for industry to respond and create this capability to increase far beyond 10 and 12. So we can meet our internal demands and also become a potential commercial launch service provider. GSLV continues to be a successful now. You know about the last 3 successful flights, and it has been declared operational from the GSLV-05 mission, where INSAT 3DR, you heard the climate satellite, was launched successfully in this mission. And the forthcoming mission is GSAT-F09, where it will be launching GSAT-9 satellite, and this launch will happen in March 2017. The capability today for GSL is around 2.2 tons, and this will be progressively increased from 2.2 to almost 3 ton, maybe 3 ton plus in the coming years. We have a technology growth plan in this rocket, and at least 10 of these missions are scheduled. I am not going into those details of it. GSLV Mark III is our new rocket. We have a mission in 2014, it's experimental mission. This experimental mission was without the upper cryogenic stage. It has a big solid booster, a liquid upper booster stage, but the cryogenic stage what we put in that mission was a very inactive one. But we had a payload called the CARE, and that demonstrated the whole design of the rocket through the flying through the atmosphere. So today we have the cryogenic system C25 stage, which uses liquid hydrogen, liquid oxygen at very low temperatures, and then creating thrust of almost 20 ton by the engine. We call that engine CE20. That engine has gone through all the test programs last year, and we are getting ready for the stage which is shown there in the middle of the picture. That is called the cryogenic stage. It will be tested in this January itself, and we are getting ready with the flight for this before this March end itself. So this will be the first development flight to cryogenic stage in the GSLV Mark III, and with that we will have a capability of 4 ton to geotransfer orbit. It is going to increase significantly, almost double the capability of launch vehicle capability today. Yet another exciting development taking place in ISRO is the semi-cryogenic engine. You know, semi-cryogenic is a system where liquid hydrogen is not used. Instead, we are using kerosene, a modified version of kerosene, which is a little bit refined version of kerosene, along with the liquid oxygen. The advantage here is that it is less complex than the cryogenics. We can load more propellant because hydrogen is very dense, not a dense liquid. It requires large volume to store. Once you go to kerosene, we can store very large quantities of kerosene. Thrust can be very high. They are very good use for boosters of rocket, and it gives you very high density impulse. That is, for the given density of the system, this semi-cryogenic is the highest impulse compared to a cryogenic engine. So they are best suited for boosters, and we are developing a booster stage called SC200, and that will going to power our future rockets. And once you have this engine, we are going to build bigger boosters called SC400, ultimately making very simple 2-stage rockets which can take the similar type of payloads as being done today by GSLV Mark III. And we have a roadmap using this cryogenic and semi-cryogenic stages. It is possible to create a human space flying rocket which can take almost 10 tons to low Earth orbit, which is enough for at least 3 or 4 people to travel to the orbit and travel beyond that point using this technology. The rocket will be much simpler than what you've seen in pictures recently, but this is a roadmap on which we are working, and I am sure it will achieve its goal by 2024 or so. Chandrayaan-2, the lander and rover, you have just heard about them. The GSLV is going to launch this craft in its one of these flights, forthcoming flight in 2017 or 2018 beginning. The most challenging aspect here is the increased mass of the Chandrayaan-2 compared to Chandrayaan-1, which enables us to put a rover and a lander and a rover. And you just imagine that if you have to put a lander on moon, from an orbit in the moon, you have to come down and land. Just imagine a rocket after launching the spacecraft coming down and landing in Earth. We have not even demonstrated that. We don't have a landing rocket. But here we are going to take a craft to moon and make it land in moon. The advantage there in moon is that the gravity is only 1/6, so we can manage the lesser thrust. So, but still we need an engine or a liquid engine that is able to take the craft, reduce its velocity, come very slowly and do a very precise maneuver on and then touch the ground on the surface of the moon without breaking the whole thing. So the engine which we are developing today is an 800 Newton engine, having 4 of them being throttled to match with the velocities which are required, move it horizontally, find out the best place to land without boulders and crevices, then land it safely. So the autonomous navigation system to do the landing, the propulsion system to do this landing process, all these are being developed now. It's a very exciting mission what VSSC, LPSC and our satellite center are jointly trying to develop. You would have heard about these 2 important missions, reusable rocket flight and air breathing propulsion through newspapers. I am sure you would all have read about it. The winged rocket which you see on top of the solid booster, this was a very unique craft which we designed, where we put that aircraft technology into a rocket technology, and we put that craft into a suborbital flight. It did the maneuvers, it came back with the aerodynamic control, and demonstrate a landing sequence on top of the surface of the sea. Okay, we didn't have a runway to land it there, but then we demonstrated that it is possible to work with the software and then do an autonomous landing. Just imagine an aircraft which India has developed where there is no pilot required. You know that even in a commercial sector itself, we don't have an aircraft of our own. We are still buying those aircrafts. But you look at the scenario today, a hypersonic flying aircraft we have designed, it is being flown without a pilot autonomously, and we are able to land it. It's a really high technology which you have demonstrated today. And this is only in a scale model. It is not the actual aircraft that will fly or a spacecraft that will fly. Meantime, we have done another important technology demonstration that is called air breathing technology, which is on the picture just below that. It shows the flight of two of the air breathing engine in one of the sounding rocket. What you have seen here is in a hypersonic flight. Hypersonic is something like 5 times the speed of sound. When the air flows through the engine, without rotating parts in the engine, it is possible to compress the gas, combust in the products, then generate positive thrust. So this has been demonstrated. The advantage is such an engine, if you have, it is possible to make use of the atmospheric air, then use it as an oxidizer, then generate thrust, thus bring down the mass of the rocket in the future, a reusable air breathing rocket. So a combination of reusable rocket with wings and a air breathing engine, it is possible to create a very low cost, cost effective rocket at some time. And that is what we are now currently working on. This rocket has to dwell in the atmospheric regime to gain velocity, and once that part is over, it will convert itself into a rocket and take it to an orbit. So this is what a challenging opportunity that is coming in front of us with the success of these two important technology missions. One of the important capability that we wanted to develop for a very long time is the human space flight capability. So human flying to space is always has been our dream, and ISRO is getting ready, equipping ourselves for an ultimate capability of human space flight. So what are the elements of this capability? One, of course, is a launch vehicle. We must have our own rocket, and that must be highly reliable. We call them human-rated launch vehicle. One of the essential elements of a human-rated launch vehicle is the simplicity, and also the ability to test and before we fly. So liquid engines provide you that capability, and that with that we will be able to make a simplified rocket. We need to create crew escape system. If at all the rocket fails, it is possible to save the crew, bring it back to a safe zone through another rocket system through parachuting. So that is getting developed. We are developing an orbital vehicle which will carry the crew through a propulsion system in an orbit for a few days of sustained flight. So we will put inside a rocket and demonstrate that it is possible to have such a mission without crew inside actually first. Maybe a few missions we have to go through without crew. Then we have to conduct a pad abort test. Pad abort test is an important test where the crew escape system is tested. You imagine that just before the launch, the rocket is going to explode. Have you seen the SpaceX failure before filling time? Such an eventuality happens, the rocket is going to burst at this time. A small warning comes and this system takes you away, at least 2 kilometers away from the rocket, so that crew is saved. So we are going to do this test in just few months from now, and this is just getting ready. So in addition to many other technologies like life support systems, waste management, crew glass, mating and connecting systems, so many technologies we are working on, but ultimately all this will feed into a human capable launch vehicle systems in the future. Another important element is the infrastructure. While we do all this, where is the facilities, infrastructure in this country to do such a complex technology? As Dr. Shivan in the initial remarks said, the Cold War brought in technologies of space in European and other countries, whereas in India, space came from applications, whereas there the applications came from rockets. The rockets and missiles existed there, from there came the satellites, from there came the application. But India, just the reverse. Applications came first, then we became the satellites, from there came the rockets. So we never had a proper industrial infrastructure in this country to build rockets. But it is coming up in a small way. We are creating capability within ISRO in terms of launch pads. Now this facilities at Sriharikota is getting expanded. All through the country, many industries, almost 200 industries are participating, and we are asking them to get ready to take up bigger responsibilities. I would like to summarize my presentation by telling you that we have a very clear roadmap on how we need to go through the launch vehicle spacecraft technology. One direction is to bring down the cost, is to enable new technologies into it, and another direction is to increase the payload capability substantially from the present 2.2 tons to almost 10 tons or even excess of that. The third direction is to simplify the rocket technology in terms of reducing the number of stages, bring in testable systems, bring in very modular concepts, and ultimately create human-rated capability for launch vehicles. PSLV will continue to remain as a workhorse. We need to increase the number of production and then launch and meet the national demands of remote sensing, and GSLV 2 to meet the national demands of communication. That itself we have a large backlog which we have to build up. So that is a thrust that we are working on, and I am sure with your support, with the government support, with the people support, these visions will be achieved. Thank you so much.